So what we'll talk about is three coloring of graphs. So the input to this problem is a graph, and the desired output is a legal three coloring in which for every edge the endpoints are colored differently. So this is an NP-hard problem. So what this really means is that for every polynomial time three coloring algorithm, there is some input on which it fails unless p equals np. And what we are interested in is studying frameworks in which we can distinguish between easy and difficult instances for this problem. The framework we'll describe here will be specialized for three coloring, but it can be generalized to other problems as well. So our framework is the following, the hosted coloring framework. And in this framework, the input instance is determined by two choices. First one chooses some host graph H. And then within the host graph H, one plants a legal coloring, not necessarily legal, so every vertex receives a color. And then edges which are monochromatic, we remove them from the graph, and then the coloring that we planted becomes a legal coloring. And this is the input to the algorithm without the coloring, of course, and the algorithm needs to find some coloring of the graph. So we have some choice of a host graph H. In it, we plant a coloring. It does not have to be a legal coloring. Some edges might not be legally colored. And then we see which are the monochromatic edges. We remove them from the graph. We remove the coloring. And this is the okay. And this is the input to the algorithm. Okay. Okay. So this is the model. So within this model, the algorithmic challenge is the following. The input is some graph G that we get from this procedure. The algorithm never gets to see the original host graph H or the planted coloring P. And the goal is to legally three color this graph. And let me emphasize here that the algorithm does not have to output the planted coloring. Any legal three coloring is okay. So within this framework, we can have several models. The most naive one is the one in which the adversary selects the host graph, the adversary selects the planted coloring, and we just get an adversarial graph, which is the worst case instances. Yes?
So in the planted click
yes.
kind of problem, in that case, you actually look for the same click that was placed in the click.
In that case, usually in the planted click, for the range of parameters that we are interested in, the planted click is the unique optimal click. So if you find the maximum click, it would be the planted one. Here, depends on the model. Sometimes it will be, the planted coloring would be the unique coloring, sometimes not. So when it's not, it's okay to present a different one.
I think also in the planted click, it's okay
to there are no other clicks of that size. Yeah. Okay, so the case where both H and P, the host graph and the planted coloring, are adversarial is not that interesting for us. This is just a usual worst case instance. A different special case of this model was studied extensively. In that case, the host graph, it's equivalent. I mean, this was not the way this model was originally formulated, the one I'll describe here, but that's the way I'll describe it now. So in this case, the host graph, you can think of it as a random G and P graph. So every edge is present independently with probability P. And the planted three coloring is random. Each vertex at random, you give it one of the three colors, and then you remove the monochromatic edges. So this model is exactly the same as a model introduced already in the 70s by Kuchera, which was called the GNP-K model. K in our case is 3, K is the number of colors. And that model was described as if you have three color classes which are independent sets, and between them you put edges at random. It's the same thing as what I described. We will use the notation G and D, where D is the average degree of the graph instead of G and P, because it would be more convenient for us to parameterize random graphs by their average degree rather than by the edge probability. But of course, these things are interchangeable. So our random version can be denoted as GND3. So it's a random graph of average degree D in which you plant at random a recoloring and remove the monochromatic edges. So the average degree becomes something like 2D over 3 after you remove the monochromatic edges.
So when you say here, random means also uniformity. So the groups are same size.
Yes. So if you select the color classes at random, the vertices, each one gets a color independently, uniformly at random,
so
then they're roughly of the same size.
On K because it's
Yeah.
roughly.
Yeah, so they're roughly the same size. So they don't have to be exactly the same size, but they will be roughly the same size. Okay, so to get some intuition, so this is a well-studied model. I just want to present some intuition about this model. So let's suppose that D is very large in this model. So think of it as, let's say, nearly linear, okay? Then what we'll have, so this is always true. So two vertices of the same color class, if D is large enough, okay, would have neighbors, common neighbors in the other two color classes. Let's say if both of them are red, then so they can have common neighbors in the blue color class and in the green color class. And if vertices are in different color classes, let's say one in red, one in blue, then they have common neighbors only in the green color class. So they have fewer common neighbors. So in this case, a simple algorithm would be, when D is very, very large, to put we pick a vertex and ask which other vertices are in the same color class as V. Those which have a lot of common neighbors with V would be in the same color class. And when D is large enough, significantly larger than square root n, this recovers the planted coloring. So this is a very simple algorithm, I think observed by Kuchera. This was later strengthened by Bloom and Spencer. So they could extend it to the case that the average degree is n to the epsilon for any epsilon. And the idea was, rather than counting common neighbors, at this density there are no common neighbors, typically of two vertices. What they do is look at neighborhoods at larger and larger distances. And the range of answers that you get depend on whether you're on the same color class or a different color class, and you do the computation and it works out. And
So
yes.
here the running time would depend on epsilon or not?
Not really. I mean,
Why not
it's
taking epsilon to be sub?
because the probabilistic analysis will not work. When you start counting common neighbors at distances too long,
I guess.
because it's in a sense, you make a random walk from these two vertices, and once it mixes, you lose like the original color classes in a sense. You have to stop before the random walk mixes. So let's say a very important development is this algorithm of Alon and Kahale from 1997. So they presented one result, but I'll break it into two. So one of them is that a spectral algorithm. So you look at the adjacency matrix of the graph, compute eigenvalues and eigenvectors that correspond to them, and from them you recover the coloring. So one of them is that a basic spectral algorithm finds the planted recoloring whenever the average degree is larger than a constant times log n. At this point, this is the planted coloring is still the unique recoloring of the graph. And then they show that even at smaller values of D, at this point, the planted coloring is no longer the unique recoloring. A polynomial time algorithm that starts with a spectral approach and then does additional steps afterwards manages to legally color the graph, provided that D, the average degree you start with, is some large enough constant.
Here the coloring will still be correlated with the or planted.
It will be correlated with the planted coloring, but in general it would be different. In particular, that would be isolated vertices that you can color any way you want at these densities. But of course, other smaller structures can change color.
So the C only depends on the L that you want?
In the
So the C, the constant, just the
Yeah.
L, essentially?
So below a certain constant, we don't know how to prove this theorem.
Or like a universal constant?
Yeah, there's some universal constant, let's say, I don't know, 100 or whatever. Above it, it works. Below it, the analysis like breaks down. And it's an open question, what happens below it.
Is this the result that stays the same if it was a random regular graph? Degree?
Yes. In fact, some things become easier if it's regular, sometimes, in some models.
The concept is probably different.
Yeah, so in some models, things become easier in the regular case. I mean, the analysis may be, sometimes it's more complicated to argue about regular graphs, but the constants usually improve.
Do you
Yes.
need only to know that there is a recoloring and that this is the lower bound of the degree, or you need to know that this planted tree?
So it has to come from this is a particular distribution on three colorable graphs. The algorithm is tailored for this particular distribution.
It's a random graph. It's with high probability.
Okay, I missed all results almost surely for random choice of G and P. Okay. Of H and P, really. H and P. Yeah.
So these results from the block model, if you make them specialized to the case of coloring, I think it says that if D is more than 1 over K times K minus 1, where K is the number of colors, then you can find coloring that is correlated with the planted one.
Okay, you say that, in fact, this value of C, there's better analysis since then. That
And it's tight.
Uh-huh,
I mean, it's
okay.
configured to be tight based on like replica symmetry breaking. But
Okay.
this is proof that you can go down to
Uh-huh.
1 over K times K minus 1.
and this holds also for small k, like
So
3.
only K.
Okay,
You're
like
starting from 2.
Oh, okay.
K approach. Yeah.
Uh-huh. And okay. So the question that we ask is which aspects of the randomness are needed in this result of Alon and Kahale? So there are two sources of randomness in the model. So one of them is the host graph was random. So the question is, can we replace it just, let's say, by an arbitrary expander, and would the result still hold? And the other is that the planted coloring is random. So for example, is it okay if an adversary looks at the host graphs and then plants the coloring with equal color classes, equal size color classes? Does the problem become more difficult then or not? So what we'll do through this talk is review this algorithm of Alon and Kahale at a very high level and sketch its analysis. Then see what changes when the host graph is an expander rather than a random graph, and what changes when the planted coloring is adversarial rather than random. And then present some open questions that I think are very interesting. Yeah.
Is it possible that, I mean, is it NP hard to color a three-colorable expander, like a worst case expander?
So, okay, you have to define expander. Under some definitions, it would not be three-colorable. So, it depends how you define the expander. Like,
It's like the
Yeah.
color number is at least 12.
So
in a round.
so you can have things like bipartite expanders or things like that. But I mean, so in a sense, we'll get to something like this.
No,
Yeah.
you take your K groups and then you put bipartite expanders and it's well defined.
So in a sense, what we'll do to some extent, we'll answer questions like this. So maybe let's go on, and if the question remains, then ask at the end. Okay, so to understand the algorithm, it's good to have some notions of different kinds of coloring. So P is the planted coloring. We'll have a notion of a B approximate coloring. So this is a coloring which is not necessarily legal, and it agrees. It has, let's say, small Hamming distance from the planted coloring, so it agrees with the planted coloring on all vertices except for B vertices, and think of B as something sublinear, let's say. A safe B partial coloring is something even better. So you don't color all vertices of the graph, you color only some of them except for B vertices, but all those vertices that you color exactly as in the planted coloring. So it's safe. From then on, you can always continue. You have made no mistakes so far. And a legal coloring is any legal coloring, not necessarily the planted one. Another notion that will help us understand the algorithm is the notion of good and bad vertices. So if we look at an arbitrarily here roughly d-regular graph and planted it a random tree coloring, so what we expect every vertex to have roughly d over 3 neighbors of each color class. So a vertex is good, or typical if it satisfies this property, and some small fraction of the vertices might be bad in the sense that their neighbors and is going to be exponentially small in D. So this is the notion of good and bad vertices, and now we can describe the algorithm.
B is the same B you will use.
B would depend on the context.
No, I mean the B from the previous slide and this B are
Will be related. Yeah. Okay, so these are the steps of the algorithm of Alon and Kahale. So the first step, I'll give a few more details later. So the first step is some spectral clustering. So we look at the adjacency matrix of the graph, do something with it, and based on it cluster the vertices. And this would give an approximate coloring. So some fraction of vertices would be clustered incorrectly. Later, there are some local improvement steps in which the fraction of vertices that are clustered incorrectly or colored incorrectly drops down dramatically from something inverse linear in D to exponentially small in D. Then there's an uncoloring step. Every vertex that we suspect that we maybe have a mistake on it, we uncolor it, and we can show that this results in a safe partial coloring, meaning that every vertex that remained colored is indeed colored exactly as in the planted solution, and only few vertices are not colored. And then, because so few vertices remain uncolored, we can finish with dynamic programming that gives a legal coloring, not necessarily the planted one. So let me give now a few more, maybe one more thing to note. If D is larger than log n, then already after the local improvement step, already here, the fraction of B is so small, it's below 1, so already we get a legal coloring after the first two steps. We don't need to continue with the other steps. So, and we get the planted coloring. Okay, so let's give a few more details, not much, about each step. So for the first step, spectral coloring, we look at the adjacency matrix of the graph. In fact, not exactly the adjacency matrix. So if D is very small, we remove some high degree vertices to begin with, so they will not skew the spectrum. Look at its eigenvalues, and we compute the eigenvectors corresponding to the smallest two eigenvalues, the most negative ones. And then each vertex, if we look, has its value in each one of these eigenvalues, so it's like an embedding of the vertices in the plane, if we look at these eigenvalues as a coordinate system. And then we just do clustering, some distance-based clustering on what we get. And it can be shown, I'll not give the details, that this gives something very well correlated with the planted coloring. So the fraction of vertices that we need to move between the clusters to get the planted coloring is only 1 over the degree.
Vertices in the same color clusters will be very close to each other.
Yeah, typically they would be very close to each other. So as a picture, what we get after this first step is this large region. Most of the graph is green, colored exactly as in the planted coloring. Green corresponds to colored as in the planted coloring. And there are some smaller regions which are colored incorrectly. The next step is a local improvement, a very natural thing to do here. So every vertex can check locally whether it appears to it that it's colored correctly. So it checks how many neighbors it has from its own color class and how many from different color classes. And if there's some other color class in which has fewer neighbors, it wants to change to this other color class. So you do these local improvement steps And it can be shown that this reduces considerably the number of miscolored vertices. And in fact, it relates now to the number of bad vertices that we have in the graph.
So here you can choose any order?
So the analysis goes when you do it parallel step by step, but presumably you can choose any order. I'm not sure if in adversary, we have to check it, some of these things. If there's some careful order in which the adversary can fool you. But the analysis works, does it like everyone who's not satisfied in the previous step in parallel changes its color and you repeat. That's
Like
but,
in iterative decoding.
yes, yeah. So you start from a situation like this and you shrink the bad areas. That's what happens here. In the next step, you do a cautious uncoloring. So every vertex that suspects that maybe something is wrong with his color, why would he suspect it? Let's say it has too few neighbors in some other color class. So it thinks maybe accidentally I should have belonged to this other color class. So every vertex that suspects that something is wrong, it just uncolors itself. And what this results in is in a safe coloring. So this is something that needs to be proved, that every vertex that remained colored, indeed his color is exactly the same as in the planted coloring. And in a pictorial way, what we really get is that these bad areas grew a bit bigger, but now these vertices are just not colored. It's not that they fool us by having a different color, they just don't have any color and we need to color them. And the last step is a dynamic programming step to color these regions which are uncolored. And the most important theorem here, and this is maybe, if you look at what's the most difficult proof in the paper of Alon and Kahale, is proving this fact at the end. All the others are also innovative, but technically, I'm saying, if you look at the most difficult technical part, is to show that in this step, each one of these components size, if you look at these as connected components in the graph and no edges between them, each one has size order of log n. So they are very small and you can color each one of them individually by exhaustive search. So this is the main theorem with respect to this step, and then you can complete the coloring. So we started with this safe coloring, and then we completed it to a legal coloring, not necessarily the planted one. So the colors, in terms of the code here, this is colored correctly, but not necessarily colored legally, but not necessarily the same as in the planted coloring.
So that's what you said, that in the log n regime, then this would not
Yes.
be the same, actually.
Yeah, in the log n regime, you don't need the last two steps. Already after the first two steps of the algorithm, the whole graph is legally colored. So these are, again, the summary of the steps of the algorithm of Alon and Kahale. And now what we will ask ourselves is the first question we ask ourselves is, does the host graph need to be random for this algorithm to work? So if we look at the details of what this algorithm uses, so the first step, spectral clustering, hinges on the following fact that in the host graph, there's no eigenvalue which is very negative, more negative than minus d over 3. After you planted recoloring, there is such an eigenvalue. So this is what you use in the spectral approach. And the analysis of other steps uses expansion properties of the graph. I didn't show the analysis. And this is captured by requiring that the second largest eigenvalue of the host graph is much smaller than d. So if we look at lambda as the minimum of the second largest eigenvalue and the absolute value of the most negative eigenvalue, then suppose that the adversary is allowed to pick an arbitrary expander h, not random anymore, worst case, but under the condition that this second eigenvalue is small, much smaller than the first one, which is d, so smaller than d over 30. So some spectral expander, and let's keep p, the planted coloring, random. Can one still three color such graphs? So that's the first question that we ask ourselves. So here is our algorithm for doing it, which is exactly the same, you can say, as that of Alon and Kahale.
The answer is yes.
So the answer is yes. And but there are some okay. So basically the same algorithm works, but you have to work a little to prove it. So if you look at the major steps that we do, they are the same, but the details within each step are different, sometimes in the analysis and sometimes in the implementation of the steps. And why are they different? Because first, in the analysis, we can no longer use the fact that the graph is random, and this was used in the analysis of Alon and Kahale, so we have to replace some steps in the analysis. Another thing that changes is the expansion that we have is much smaller than that of random graphs. So again, we need to strengthen a few things. So these things cause some changes. So let me discuss just perhaps the most interesting change that happens in the analysis. So recall that we reached a step after the third step of the algorithm of Alon and Kahale. We reached a safe coloring where only few vertices are colored incorrectly. So this is the safe coloring, and we need to complete it to a legal coloring. So, so B would be something exponentially small in D. So the n over 2 to the D. So if D, let's say, is a large constant, so this white area is really a linear fraction of the graph. If D is larger than log n, then it doesn't appear at all. So these are the bad vertices. Those are the fraction of neighbors that they have in some color class deviates a lot from what you'd expect. Okay, so the main reason why they could complete the analysis was that they could show that each one of these connected components is smaller than log n. So this was perhaps the most complicated part, as I said, of their proof, to show that indeed these components of free vertices, that those which are uncolored at this stage, are small. And to try to prove the same thing for our algorithm becomes much more difficult because we are not in the random graph setting, and it becomes more difficult to argue about it. So we circumvent the need for the above theorem and replace it by something else. So like an observation that they did not need, we can do it and save a lot in the analysis. So the point is that even if connected components are large at the end of this stage, we can complete the partial coloring to a legal one by the following additional step, which is safe recoloring, a very obvious step to do. So if you have some vertex which is uncolored and you have it has neighbors in 2 other color classes, then you know for sure what its color has to be, because you know that you did not make any mistake with the vertices that are already colored. So you can just color it. So of course, it's an obvious step to do. The point is that we can show that it very much helps in the analysis later. So the new version that we have is that when you can no longer continue with the safe coloring, then the connected components of the free vertices have size. Okay, so log n times some constant smaller than 1. Okay, that depends on the expansion of the graph. So the main point is that it's not more than log n, and hence we can also complete the coloring by dynamic programming. So our proof uses only randomness of the planted tree coloring and not of the host graph H. The host graph can be an arbitrary expander. It turns out not too difficult to prove it if H is a strong expander, meaning that lambda is very small, order square root of d. It's more tricky if H is only a mild expander, so if lambda is some small constant times d. And let me just show a main lemma that we use here, so which helps in doing some union bounds. So I don't know if you know this lemma or not. If not, it's worth knowing it. It's the following, that in every graph, the number of connected components of size k with t neighbors, So you look at a connected component that has k vertices, and the number of other vertices that are neighbors of this connected component is exactly t. So this number is at most, so n choose n over k, forget about it. That's not so important. So this is n is like there are n starting vertices to
Just a second. Is the number of connected components of size k?
with t
Connected
neighbors.
components have no neighbors outside themselves. Right?
No, okay. I mean, you look at the whole graph. You look at, like, take a subtree of size k and look at all the vertices that touch it from the outside. This is what I mean.
Connected components. You
Yeah,
just look
connected
at the
subgraph.
sides.
Connected subgraphs. Yeah, not component.
But,
Okay, connected subgraphs. Sorry, or connected sets.
Not necessarily disjoint, just connected subgraphs.
Yes. So the number of connected subgraphs,
Size
you
k.
count all of them in the graph. So the point is, think of k as roughly equal to t. So this is just exponential in k times, let's say, n. So you can think of n starting vertices, and around each vertex, typically, each vertex is involved only in a number of such connected subgraphs, which is just exponential in k, regardless, let's say, of the degree. The degree can be arbitrary here. It has nothing to do with the degree, nothing to do with expansion of the graph or anything else. So this is true for any graph. And this is like a very useful lemma when you want to use union bounds on the number of connected components with a certain number of neighbors, as we need to do also in our proof.
So with t neighbors with that more, we should think of this k and t are upper bounds?
No, of exactly k, size exactly k and k.
understand,
Yeah.
but I mean,
In the proof?
What is the condition that prevents it from being larger?
No condition. That's true for
I
every.
understand.
Yeah. Sorry, don't. Yeah.
Is it true if I said the common components of size at most k with at most t neighbors, the bound is still correct?
You can do a union bound over all smaller k and
So
t.
it's not-
That's what you do. Yeah. So this is exactly k and exactly t. So think of it, let's say, if you didn't count the number of neighbors, let's say this number of connected subgraphs of size k typically would be something like, if you look at the vertex, it has d choices of neighbors, so it would depend on the degree d, for example. Typically it would be something not like 2 to the k, maybe d to the k, or things like that. So this is a much better bound.
If you have few elements, because you can have like d times k.
So you can have
It
like
would be like d times k.
just the number of paths, you can say, starting at a vertex, or the path of length k would be something like d to the k, or k to the d.
You're saying this estimate is better when t is like much
Yeah.
smaller than.
Yeah, so, yeah, okay. So, I mean, this helps in some range of values, this helps and is used. So, I just,
So what happens with the path of length k? So there are d to the k of them, but they don't have k.
so the question is, can they have exactly t neighbors? Because the point is that,
Neighbors were
so outside the path,
outside the path.
so exactly t. So it's exactly t. Okay, if they are more or less, we don't count them.
Fine.
So several proofs of this. So this is a theorem, a lemma that is very useful, and I mean, I, like myself first, I think, proved something like this in the 90s, and I know of other people who proved later, but Noga alone points out that this is a special case of a theorem of Bolabash on intersecting sets from 65. So certainly it's, I mean, theorems like this were known long ago. So just something to keep in mind. It comes useful in certain proofs. Okay, so now I'll move to a different question, which is, any questions?
Just before your host graph H was an expander, but
Yes.
you said it was what? The degree was not constant.
So in our case, we think of it as a, let's say, expander of, let's say, degree d or degree roughly d. Doesn't really matter if the degree is exactly d.
Yeah.
And d does not have, it can be either constant or larger.
If
Yeah.
it is constant,
Yeah.
if you freeze the degree, it should help a lot because you don't have this outlier eigenvalues, right? Compared to the
Yes.
Schwenny case where you have
Yes,
magnitude.
yes.
So in a sense, you should be able to, without having to regularize the graph or anything, get
Yeah.
directly.
Yes, so you don't need the step which is done in Alon and Kahale, which when D was small in Alon and Kahale, they said we don't compute the eigenvalues of the original graph. We, let's say, throw away the vertices of high degree,
Okay,
then
you
do
don't
the
have-
analysis and then put them back in.
you don't have-
We don't need to do this here, no. Okay, so the second question that we ask is, does the planted coloring P need to be random? So the model is as follows. First, the host graph H is selected, maybe as an expander or as a random graph. Then after seeing H, an adversary selects a balanced recoloring in it. So partition the vertices into 3 roughly equal size sets and removes the monochromatic edges. So this is the setting. So the adversary gets to see the graph before planting the coloring. Does it help the adversary make the problem more difficult? So here what changes? So this notion of good and bad vertices that played an important role before, here there's a big change. So if D is a host graph, if H is the host graph and it's D regular, then recall that we said that after the planted coloring, we say that a vertex is good if roughly D over 3 of its neighbors are in each color class. Now, if P is adversarial, then the number of bad vertices, before it was exponentially small in D, regardless of the input graph, as long as it was D regular. Now it depends on the expansion of the graph, the fraction of bad vertices. And, there's some, so only if lambda is smaller than D, we get anything, okay? Significantly, if it's not an expander, the adversary almost all vertices can be bad. But if it's an expander, there's some control. It cannot be that all vertices are bad. Only a small fraction is bad. The smaller lambda is, the better. So it's not, the fraction of bad vertices is not as small as it was before. Before it was when the host graph, when the planting was random, the fraction was exponentially small in D. When the planting is adversarial, the fraction of bad vertices is small, but not as small. And this makes a big difference. So here's an algorithm, the same algorithm of Alon and Kahale. How would you try to run it for the case where the planted coloring is adversarial? So you do the spectral coloring, and now if you do the analysis, you can show that you also get an approximate coloring, but the parameters are not as good as before. The fraction of of miscolored vertices, those who receive the wrong color, is lambda over D rather than n over 1 over D. And lambda is always at least square root D, so it's worse. Then in the local improvement step, you do reduce the fraction of badly colored vertices, but not as good as before, not exponentially small in D, but only this much. The cautious uncoloring, again, leaves roughly this fraction of vertices uncolored, and then you do the dynamic programming. So let's see what happens with the running time. So the first 3 steps take polynomial time as before, and the only question is what happens with the last step, the dynamic programming. Does it take polynomial time or not? For example, are the bad uncolored vertices, do they only form small connected components, or might they form large connected components? If they form large connected components, can we still color it, yes or no? Okay, so the situation is that we have already colored almost all the vertices of the graph exactly as in the planted coloring. We left a few vertices uncolored, and we need to complete the coloring. Is this difficult or not? So here we have a hardness result, and we have several, and this is like the most interesting one, which is the following. Even if the host graph H is a random G and D graph, not an adversary, not an expander chosen by an adversary, then if the planted balanced recoloring P is adversarial, the adversary chooses how to plant the coloring, he can choose it in such a way that recoloring the resulting graph is NP-hard. So there is a way of planting a coloring in a random graph in which the finding the coloring is any legal tree coloring is NP-hard. So the proof does not work for all ranges of the degrees. Interestingly, it just works for this range. So when the degree is n to the delta, where delta is between 0.4 and 0.5. So when think of the degree is slightly smaller than square root of n. When the degree is much smaller, we don't know. Much higher, we know that it's incorrect, this theorem. And what's nice about this theorem is that it's a rare example where NP-hardness can be proved on instances that are mostly random. So almost everything about this instance looks random. The adversary does have some choice here of how to plant the coloring. And this is enough to make a problem NP-hard. So usually in models that involve randomness, sometimes we do say that we think that this problem is difficult because otherwise we can prove have an algorithm for some other problem like planted clique, which is also defined with randomness in it. So here we have a worst case hardness assumption, proof. Yeah. So here's a sketch of how we can prove such a thing. So I'll not give all details, but just the main idea. So suppose there is some algorithm, let's call it alg, that can three-color graphs G generated from any random G and or most, okay, not any random G and D graph, most random G and D graphs H, and any balanced planted three-coloring in them planted by an adversary. So we would like to use it on some other graphs. So let Q be a small sparse NP-hard graph that we want to three-color. So what we'd like to do is give this hard graph Q to the algorithm and ask the algorithm to color it and claim that the algorithm indeed colors it. So if it colors graphs from this somewhat random distribution that we had here, it would also necessarily be able to color for us our small graph Q.
So this Q will be what results from the...
So I'll show how we get this Q a little. And now the question is, why would the algorithm color this Q? Like, how do we fool it to think that it should color it? Because it looks as if it's coming from a very different distribution. So here's how we build the algorithm, input to the algorithm. We don't just show him our graph Q that we want it to color. Next to it, we append also a large random graph in the G. The number of vertices in this random graph, instead of being n, is n minus the size of Q. So this contains all the remaining vertices, completing the number of vertices to n. And this is just a random like G and D3 graph. So we have a G and D graph, a random graph, which we partitioned into three color classes and remove the edges within each one of them. So this is what we give it as input, the algorithm. And we ask it to color it. Of course, the algorithm sees that Q is here on the side, like something is fishy about the graph. But we claim that it has to color it anyway, because as far as it is concerned, it may have come from the following instance. So the instance we may have started with is the following. That really we started with this huge, large graph that was composed here of a random G and D graph, and Q was maybe part of this random graph, and in it an adversary planted a three coloring. So this is how we got this Z prime. And because of this three coloring, and Q was three colorable to begin with, so the adversary did not need to plant anything in it, but because he planted the three coloring in such a way that all neighbors of the red region in Q, because it's small, this graph Q, all the neighbors are less than 1/3 of the graph. All of them were colored red here, and so these edges dropped, and all the neighbors of the green colored vertices here were colored green here, and so on. So these edges were dropped, and this is what we got. Okay, so this is what we want the algorithm to think. That when it gets this input, we want it to think that it came from something like this. So that's not exactly the end of the story, so let's give a few more details.
But the best would be
Yes, so we need to show this. Okay, so I'm getting there. So we have a three-colorable graph Q on n to the epsilon vertices, and we want our algorithm to color it for us. So what would the adversary do? Well, so let's describe what the adversary do and what we do in the simulation. So what we do in the simulation I showed you. We just give the algorithm a disjoint union of Q and of a Gn prime D3 graph. This is what we do in the simulation. What does the adversary do to produce something similar to the simulation? So it gets an input H from G and D. In it has to find a copy of Q, if one exists. Then it has to plant in H minus Q, in the remaining vertices, a three-coloring, which agrees with colors of neighbors in Q, like to do this thing that, so this was the whole graph. It had to find in it a copy of Q, and here to plant a coloring that would cause these edges to drop, so as to get this picture. So this is what the adversary has to do, and this is the simulation. So the first question is, when is the adversary feasible at all? When does a copy of Q even exist inside H? And is it possible, and it's possible to cause the edges to drop? So first of all, to cause the edges to drop, you need D to be smaller than square root n, because you don't want vertices in different color classes of Q to have common neighbors. And the other is Q cannot, and this requires Q to be sparse already, and Q cannot be too sparse because you want a three coloring of Q to be NP-hard, so the average degree in Q has to be at least 3, and this really says that the average degree has to be at most 4. So there's a certain range of values of how we can choose Q. So here's our main hardness proof. So the graph G obtained by random G and P graph with adversarially planted three-coloring P is and it's adversarially planted by looking for Q in it and then coloring the rest of the graph in such a way that edges between Q and the rest of the graph drop. This is statistically indistinguishable from the disjoint union of a balanced graph Q. So balance means, so it has average degree 3.75, let's say. So this is some constant between 3 and 4. And it's balanced, it means that every subgraph of it also has average degree not larger than this. So we need to show that such graphs are NP-hard to color, so it's not so difficult to show it, and that they exist in every G and P graph. Every such graph, if it's small enough, it exists with high probability in almost every G and P graph. So we can show that the two distributions, one produced by the adversary and one by our simulation, are statistically indistinguishable.
Again, why do you want the degree to be less than 4?
Otherwise, it would not exist in graphs, in random graphs whose average degree is below square root n. It's similar to the thing that a clique of size 5 would not exist in such graphs. So that's a graph.
You can distinguish Q because it will have high degree or something?
Yeah, because the simulator can see that if this Q existed, it can say, okay, I mean the algorithm would say, then I know that this graph did not come from a case in which the adversary started just from a random graph. It started from something different. So there are certain conditions like, let's call them a sanity check, that you have to do about Q, about its degree, and it has to be between 3 and 4. And after that, you need to prove that these two different distributions are statistically indistinguishable, and that's the difficult part. Okay, to prove it. Okay, so let's summarize what we've seen. Yeah.
So the reason it's difficult to have the same proof for the, let's say, log n or something, is it the finding of Q?
Yeah, so if, let me say the adversary, if Q exists inside your graph, the adversary will find it because adversary has exponential time. It just would not contain.
Yeah, exactly.
Yeah, it will not contain Q.
So it will not contain all such graphs. That's
No.
the problem.
So the reduction should work the following way. I first choose a Q, and then I should say that also the random G and D graph contains Q as a copy.
Yeah, I understand.
So this is
You're taking a union bound over all Qs in this part of the,
no.
because you don't know how. Yeah.
No, yes or no, like for every particular Q, the probability that it appears in your random graph, let's say, is close to 1. I can say that. I'm not claiming that all Qs appear in the random graph. I don't need it.
I understand,
Yeah,
but
okay.
in this proof, you don't know which Q will be presented. You just want a hard Q.
Yeah, I want for every, I don't need this, okay, I'm not sure if that's what you're asking. The statement I want is that for every Q from the class that I want, the probability that it is present in the graph is very close to 1. I don't need the stronger statement that says that in a random graph, all Qs are present. Okay.
Right,
Yeah.
my only point was that
Yeah.
you start from an adversarial Q.
Yeah. Yes.
Whereas NP-completeness reductions, don't need
Yeah.
all these Qs.
So in fact, if you look, the problem is that once the density is too small, then if you look at any Q that you want, the probability that it's present becomes close to 0. So, I mean, it's... So even if you'd say, I don't know, try to start from saying, okay, I can, if I find any one of the following Qs, it would be good enough for me, none of them would be in the graph. This is really what happened. I mean, it's like a certain, like the probability that it appears goes down to 0 very quickly. No. Okay, so let's summarize what we have. So these were the previously known results. So previously people looked at the case where the host graph was random and the planting was random, and then we had these algorithms that could find legally 3-color the graph. And we're looking at the case where the host graph is an adversarial expander and the planting is adversarial but balanced, the planted coloring. So if we look at what the spectral techniques achieve, in all cases they manage to find you an approximate coloring. So in this respect, it doesn't matter if the graph is an adversarial expander and the planting is adversarial. You are able to find an approximate coloring, a coloring that mostly agrees with the planted one. The fraction of vertices on which it disagrees differs in this model, but in all cases it's a small fraction. Likewise, if we try to go to the safe partial coloring, where you are sure about the coloring of some of your vertices, and only some vertices are uncolored, you can do it in all cases, and the fraction of uncolored vertices would be small. Here it would be small, here it would be very, very small, but the same general picture emerges. The question?
I thought it wasn't true that it works the previous step in the random H if the graph is too sparse. That you would
In all cases, I'm looking for degrees, average degrees starting at a large enough constant. Okay. If it's too sparse, I don't know. So the interesting stuff happens here once we want to complete it to a legal coloring. So when the planted coloring is random, we can do it. So this is here, even if the host graph is an adversarial expander. In the case where both the host graph is an adversarial expander and the planted coloring is adversarial, we cannot do it in any degree. It's NP-hard. This I did not show. It's an easier proof than what I did show. And the interesting thing happens here. So what we know is that so here we have a random host graph and adversarial planted coloring. So what we know is that if the degree is large enough, let's say larger than n to the 2/3, you can indeed find a coloring, legally color the graph. If it's below, let's say between n to the 0.4 and n to the 0.5, it's NP-hard. In this region here, let's say, degree between n to the 0.5 and n to the 2/3 or something like that. We're not sure, but maybe it's not. Okay, we're not sure. And in this region below, we're also not sure what happened. So it's very puzzling, this situation here. So let's go to the open questions. So there are, let's say, the two questions that I find currently most interesting are the following. So the first is what happens when the host graph is a random G and D graph, but with D too small for our NP hardness to kick in. So let's say n to the 1/4, and the planted tree coloring P is adversarial. So our NP, I don't know. Our NP hard. So there is this general principle that we also always happens in these planted models, where the lower the degrees, it becomes more difficult until you get to very, very low degrees. Okay. So it should, if we follow this pattern of thought, then it should be NP hard, but the proof completely breaks down. Okay. So we don't know.
So the K was independent coloring?
So instead of planting an adversarial one, yeah. Yeah, so this question did cross our mind, but we didn't try to do anything with it. So this is one question. And another that I find even maybe more interesting is the following. Suppose that the host graph is arbitrary. So adversary can choose any graph he wants, doesn't have to be, let's say even regular, doesn't matter, but doesn't have to have any expansion properties. And the planted tree coloring is random. Can you then legally tree color the graph? So is it just true that whenever you have, you can start from here from a graph that is already tree colorable, let's say, but the adversary is still, not adversary, you are still planting a random tree coloring in it, in addition. Does this by itself already make coloring easy? So it's hard to believe that this is the case, but we don't know how to prove that it's not the case. Yeah. Okay.